Hello folks, today we're going to talk about solutions and we're going to look at what a solution is and some solubility rules. So first we want to discuss what a solution is. So back in Unit 2 we talked about what matter is and we talked about a pure substance versus a mixture. So our pure substances are made of a set ratio of compounds. They cannot be separated by physical means, but we're going to focus on the mixture side. So our mixtures are where we have compounds that can be separated by physical means, and we had our heterogeneous and our homogeneous mixtures. So our heterogeneous mixtures are where our particles are different sizes and not evenly dispersed, whereas our homogeneous mixtures are where particles are the same size and are evenly dispersed. And that is our solutions. So our homogeneous mixture is a solution. It contains some different parts. We have our solute, the substance that gets dissolved. It is present in a smaller amount. We have our solvent, the substance that does the dissolving and present in a greater amount. And then if you add the solute to the solvent and it dissolves, we will say it is soluble. For example, sugar in water. A substance is insoluble if it does not dissolve in that solvent. So there are compounds that are soluble in water. There are compounds that are soluble in oil. There are compounds that are soluble in alcohols. It all depends on the chemistry involved in those different compounds and how they interact with the solvent around them. And solutions come in all phases. A solution always assumes the phase of the solvent. And again, the solvent is going to be the component that we have more of. So a solid dissolved in a solid, an example of that would be a metallic alloy. So something like 14 karat gold. It's going to be a mixture of gold and other metals to add strength because gold is a soft metal. We can have a solid dissolved in a liquid like table salt and water. And that's going to be one of the main ones we focus on today. That's a star. We can have a liquid dissolved in a liquid. For example, adding ethyl alcohol to water. Ethyl alcohol is a liquid at room temperature, and we can pour it into water and it will dissolve. We can also look at a gas in a liquid, and that is another one we'll take a better look at today. For example, carbon dioxide and water making something like club soda. And then we can have a gas dissolved in another gas, and an example that would be air. The majority of the air around us is nitrogen, N2, but we have our oxygen, carbon dioxide, and a whole bunch of other atoms and compounds and molecules in trace amounts in our atmosphere. So we're going to look at kind of this most traditional sense of a solid dissolved in a liquid, and we'll go from there. And just as a reminder, depending on what you're dissolving in the water, you're going to give the water some different properties. So just a little recap from earlier in the year, we can have our strong electrolytes. They ionize in water. And then they are able to conduct electricity and then light our light bulb. So a strong electrolyte will fully ionize. Those are our strong acids and bases. For example, we have weak electrolytes. They conduct only a small current and the bulb will glow dimly. There is some ionization in the water, but not total. So a weak acid or a base can do that. And then we have our non-electrolytes where no current flows, there's no ionization, you cannot conduct electricity. So that, an example of that would be sugar. And if you remember, we did that lab with the electrodes where we looked at ionic versus covalent compounds and saw which ones were able to light the light bulb. I also just want to mention this, most things we talk about today will be electrolytes, and they're going to have other impacts in the future with some other topics that we talk about. So what can be dissolved in water? Water is a polar molecule, so it can dissolve other polar molecules. So remember our little Mickey Mouse shape We have our negative oxygen and our slightly positive hydrogens. And because we have these negative and positive ends, we can form attractions between other compounds. So ionic compounds, polar compounds that have that uneven sharing of electrons are going to be able to interact with water and dissolve. So water is known as our universal solvent. That should be a familiar term to you. You've seen it in biology and other science classes before. So water is a very good solvent. Because it is polar, it can dissolve other polar molecules. What it cannot dissolve is nonpolar molecules like oil. So nonpolar molecules are insoluble in polar solvents. So what affects solubility? So the first thing that's going to affect solubility is the nature of the solute and solvent. Like dissolves like is a common expression. So water being polar can also dissolve like molecules that are polar. So oil, if you were to eat something that was greasy and drop it on your clothing, a lot of times that leaves behind a stain that just washing doesn't necessarily get out. And that's because the oil and the water are not going to dissolve, and water isn't going to be able to bring that stain out. Temperature is where the majority of our focus will be today, and applying what we've learned. So for most solids, as temperature increases, solubility increases. And we'll see what that looks like on a graph soon. For most gases, conversely, as temperature increases, solubility decreases. Again, we'll talk a little bit more about that as we go on. And then pressure also has an impact for gases. So for solids and liquid solutes, there is no effect of changing pressure. Remember, they're not compressible materials, unlike a gas. But for a gas dissolved in a liquid, as pressure increases, volume will decrease and the solubility increases. So those gas molecules are being held a little more tightly together with the increase in pressure. They're able to kind of slip between those liquid molecules and solubility would increase. And with our solutions, we're going to have three types of categories when looking at solubility. We can be unsaturated, less than the maximum amount of solute is dissolved. So think of just sprinkling a little bit of salt into a pot of water before boiling it. All of that salt will dissolve, and if you wanted to add more salt, you could. It would continue to dissolve. And you could keep adding salt until it is what we call saturated. And that is the maximum amount of solute dissolved in the solvent. If you were to move on and supersaturate it, you would get more than the maximum amount of solute dissolved in the solvent, and so you would see extra solute at the bottom of the container. And you might have noticed that there's also some verbiage here below the curve, on the curve, and above the curve. So what we're going to look at in a second is a solubility curve. And it's looking at the interaction between the amount of solute and its saturation point at different temperatures of water. So let's actually look at these curves and see what we mean by below, on, and above the curve. So here's our solubility curve. It tells us how much of a solute will dissolve in a given amount of solvent at various temperatures. So here we can see multiple types of solutes. The majority of them here are, in fact, ionic compounds being electrolytes. And as we can see that we have some of these curves are more sloped than others, but in general there is a positive slope that as temperature increases, then we increase the solubility. So here you could see this green line that at low temperatures we have low solubility, but as we heat the water, solubility increases. And we use these in a couple different ways. We could look at something, let's see, let me grab. So let's look at 40 degrees. I'll just go draw a line up here so we can kind of see it. So at 40 degrees, we can look at the saturation point and the amounts that would be added for different compounds. So let's focus on sodium nitrate, this purple line here at 40 degrees. So if I add 80 grams of sodium nitrate at 40 degrees Celsius, I'm at this point here. I am below the curve, and so that is unsaturated. If I look at being on the curve exactly, at maybe like 104 grams, a little hard with that scaling, that would be a saturated solution. So I could add 104 grams of sodium nitrate to 100 milliliters of water, and it would all dissolve. As soon as I add more than that, let's say I go to 120 grams, I would then be supersaturated, and you would end up with sodium nitrate just sitting at the bottom of the beaker. It wouldn't matter how much you stirred it. At 40 degrees Celsius, no more could dissolve. So let's say I wanted to dissolve that 120 grams. What would I have to do? I would have to heat the water to a higher temperature, cross over the curve. So let's say I went to 70 degrees. Okay, well now, because I've heated the water, it's able to dissolve more of the sodium nitrate, and that would allow those extra crystals of sodium nitrate to dissolve. So with our solubility curve, we are looking at an intersection of temperature of the water and the grams of solute. So depending on those two variables, we can change something from being saturated to unsaturated. We can allow something that wasn't soluble to become soluble enough to dissolve at a faster rate. It's just really a matter of looking at the graph. So some question on the bottom here. So which compound is less able to dissolve as temperature increases? That would be this cerium 3 sulfate. If you're curious as to why, cerium 3 sulfate releases heat. It's an exothermic reaction. So if you add heat to the solution, there is going to be no energy reason why it should dissolve. So that gets a little more into some kinetics and something called equilibrium and Le Chatelier that we don't really need to deal with. But you can see that it's more of an exception than the rule. And which compound is most soluble at 10 degrees Celsius? Well, here's 10 degrees. Here's my top line. Still that purple line, sodium nitrate. Whereas if we looked at which substance is most soluble at 30 degrees Celsius, well, that would be our glucose, that red line. Okay. All right, this is just a different visualization of some other compounds with our solubility curve. So the sharper the line or the slope, the more the substance is influenced by temperature. Remember, in this dissolving of compounds, we're looking at this ionization, and energy has to be put in to break those Coulombic attractions, that electrostatic force holding them together. So some substances, depending on that energy needed, will be more or less impacted by temperature. All right, so which substance is least affected by temperature? That is going to be our sodium chloride. You can see it has a very flat slope. And this is important for our oceans and for our marine biology, that temperature doesn't really affect salt water in that way. It allows for equilibrium and homeostasis inside those critters, especially ones that might dive deep down under the surface, that don't migrate, so that in the summer and in the winter, the salinity of the ocean stays pretty stable. And that allows for our marine life to really survive the way it does. We can see several things here that actually have a negative slope: HCl, NH3, SO2. Why do they have a negative slope? Well, they can be gases at room temperature. And remember we said with temperature, a gas decreases in solubility. A little bit more on that. So here's just a graph of carbon dioxide solubility versus temperature for distilled water. And what we see is an interaction here with pressure and temperature. The overall difference here, we see that no matter what the pressure is, as temperature increases, solubility goes down. And as pressure decreases, solubility goes down. So let's think of a cold 2-liter bottle of soda fresh from the refrigerator versus a bottle of soda that's been sitting on your desk for a day. So we keep these 2 liters of bottles, 2-liter bottles of soda pressurized. You put them in the fridge. That carbon dioxide will stay in the solution and you get the characteristic bubbles of soda. When you open the cap, you're releasing the pressure, so that's going to decrease the solubility of carbon dioxide, and you're also eventually going to increase the temperature if it's just sitting on a countertop. As the heat from the surroundings goes into the soda is going to get warmer, and as temperature increases, there's more kinetic energy, and those gas molecules are going to move around more, bounce more, hit the surface, and evaporate out of solution. So why does your soda get flat? It's due to a lack of pressure and that increase in temperature. And then just a little bit on supersaturated solutions. So we can take a substance and heat it, and therefore when it's heated we can dissolve more into the water. So this is used in a couple different ways. This image on the left is making rock candy. You can also grow salt crystals. You may have had a little kit when you were a kid that used this. So sugar, remember, is a covalent compound, so it does not dissolve as easily in water. And I know we've talked about this before, but if you are a sweet tea drinker or iced coffee drinker, just dumping in granulated sugar, all that sugar settles to the bottom and you don't get a nice sweet drink. So the solution for that, see what I did there, is to make a syrup. So the way you make a syrup is you boil water, you add the sugar, you stir it around, keep adding the sugar, and because it's boiling water, you've increased the solubility. As you cool the syrup, the solution will cool, the sugar will stay in that dissolved form. But if you give it something called a seed crystal, so if you've ever made rock candy, you kind of take a rope, you get it wet, and then like roll it in sugar and then dip it in. That allows all those extra solutes that were dissolved to then recrystallize and come out of solution. So that's how rock candy is made. That's how you can grow a salt crystal. Basically make a super saturated solution, give it a place to crystallize, and those crystals can grow because the solute is going to come out of solution at those cooler temperatures. You know, it's also, if you've ever tried to make caramel, watch Great British Baking Show, making caramel tends to be an element of drama in the show because when little sugar granules get in, it causes that caramel to start to recrystallize even at those temperatures. And then the image on the right here is one of those instant heat packs. And these heat packs work on a supersaturated solution of sodium acetate. And when the precipitation reaction is started, we get this recrystallization. And that's an exothermic process that releases heat. In order to reuse this hand warmer, you put it in hot water for 10 minutes, you put the energy back into the heat pack, and then the water at the hotter temperatures is able to dissolve that sodium acetate where it remains in this state until it's triggered again. Okay. And then just a little bit on kinetics to refresh our memory. If we want to increase the rate of dissolving, we can add heat, we can stir or shake, and we can increase that surface area by breaking into small pieces. All right, we'll pause there for today and talk more about solutions next week. Thank you for tuning in. Have a great day.